Okay, so just as a reminder about what the point of this particular lesson is we're trying to identify what can we know about a differential equation if we don't know how to solve it. And so another characteristic that we can look at, aside from a slope field, is we can look at information about critical points. So critical points, if you recall from earlier math classes, these are zeros of a function or special importance. We say that the real number c is a critical point. Of an autonomous differential equation, that is to say that f, the zero of the function f, or f of c equals 0. So a critical point is often called an equilibrium or stationary point. Now, if we substitute the constant y of x equals c into an equation, then both sides of the equation are 0. This means that if c is a critical point of the equation, then y of c is a constant solution of an autonomous differential equation. This idea is going to come up when we actually start looking at solution methods, so just relax for just a second on what does that mean. But if we can find a constant that does satisfy that equation, then that constant solution we refer to as an equilibrium solution, and the equilibriums are only constant solutions. Okay, so now what? All right, so let's take a hypothetical differential equation of dp dt equals p of a minus bp, where a and b are positive constants, and the differential has a normal form, meaning we've got dp dt set equal to some function of p. Okay, and then the function of p, the only variable there is p. There's no other variable, so there's no variable t or no x, no other y. It's just one singular variable expression, so that's why we call it an autonomous. So since we're trying to have a conversation about critical points, what we want to do is we want to see are there any values of p that would give us, say, some particular solutions to this equation. So if I take that factored form, set it equal to 0, I can get p equals 0, and I can get a minus bp equals 0. And then if I solve for that, I get that p is going to be a over b. Okay, so there's potentially two critical points that we can analyze. Additionally, we can kind of create a number line to analyze what kind of behavior is going on around those two values, because those are the two values that show up as where the derivative is 0, right? So what's going on around that? And we do with something called, let's see, I think it's called a phase portrait, a one-dimensional phase portrait. And so in college algebra, when I taught that to my students, we'd talk about a horizontal line. This time we're going to do a vertical. But it's going to be sort of the same sort of setup where we're labeling where we'd expect to find these critical points. So like what's happening, let's see, which is the smaller value? Well, since we made the assumption that a and b were positive, that means a over b has got to be up here, and 0's got to be smaller than it. And then from there, we can insert some directionality, like what's happening below certain values. So let's see. Okay, yeah, I'm sorry, I'm refreshing my notes here. So what I want to point out is we've broken this up into 3 regions. We've got stuff from 0 up to p, negative infinity up to 0. Then we have anything from 0 up to AB, and then we have anything from AB out to infinity. So essentially there's 3 regions we've broken this number line up into. Okay, so let's revisit this factored form for just a second, and let's have a conversation about these 3 regions, about what we'd expect for the signs to do. So let's say I'm looking at a p less than 0. All right, that means p's negative. Well, what would that tell me about this region? So I've got a negative value up here. I have a minus b times some negative number, right? And so that gives me a negative times, and inside the parentheses I'd end up with some sort of positive value. So that tells me that before 0, our slopes would have to be decreasing at some point. So I can actually label my little curve here that away from 0, my slopes are going to be going down. They're going to be decreasing. Well, what about if it's between this a over b bit, right? Okay, so p has to be then positive at that point. That's some sort of positive value, so I got a positive thing times. And if I got a minus b times p, right? Well, it's smaller than a over b. So if I take something smaller than a over b, right? Think about if I just put a over b in there, because it's going to be approaching that fraction. That's essentially going to approach a minus something smaller than a. So if I take a minus something smaller than itself, I'm going to end up with a positive expression. Okay? So what that means is in between 0 and a over b, my slope is increasing. All right, and let's see if I can sneak in this third region. So the third region is what about bigger than that? So a over b bigger than, so anything bigger than a over b going out to infinity, right? Well, what do we know? We know p is going to be positive, so some positive number. Don't know what it is, doesn't matter. And I know a over b is bigger, something bigger. So in that factored form, I got a positive thing, and then when I have a minus b times something that's greater than a over b, right, that means this particular expression is going to be greater than a, so I end up something positive times something negative. So that tells me in this particular case that it's going to be decreasing. Okay, so hopefully that, we'll look at an example with numbers in a minute, and hopefully that'll make more sense. But this illustration, this is what we call the phase portrait. So we've labeled our critical values, and we've identified what's happening around those critical values as far as the slope goes. What do we expect in the slope field outside of those critical values? And those behaviors have certain names. So let's take a look at those individual situations and talk about what that says.